Hi everybody, my name is Ashley Azema, and I'm presenting Lab 2. In the lab, we are looking at the motion of a star orbiting a black hole of unknown mass, and seeing how well a computational model can predict the mass of the black hole. This is important because the computational model is the only way the mass of the black hole can be found, since it can't physically be measured. Therefore, it's important to study the motion of objects in conjunction with computational models for times like this. This was studied using a code in which the star's position and the star's mass were known throughout the orbit. Since time is known, the velocity was also provided. Given that mass and velocity were present, a manipulation of Newton's second law, known as the momentum principle, was the best model to find the net force on the star. With the position, mass of the star, and net force, which is the force of gravity of the black hole on the star, known, Newton's law of universal gravitation is the best model to determine the black hole's mass. Since the net force is equal to the rate of change of momentum, also known as dp/dt, the components of the rate of change of momentum can be used to determine the net force acting on the star. The two components of dp/dt are the parallel and the perpendicular. The parallel component relates solely to the speed of the object. It points in the direction parallel to the object's motion. The perpendicular component relates solely to the turning of the object. So if the object turns, it means the perpendicular component of dp/dt is non-zero. This points toward the center of the kissing circle, which is a circle that touches the trajectory of a moving object. This can be seen by the arrow pointing toward the center of the circle in the video to the right. In the video of the model of the star and the black hole, the orbiting star is the system, and the black hole and space are their surroundings. The black hole creates a non-contact force in the form of gravity. Since this is assumed to be the only force acting on the star, I decided not to construct a free body diagram. As you can see by the arrows, the closer the star gets to the black hole, the bigger the vectors of the net force parallel, and net force perpendicular get, because according to the law of universal gravitation, the closer two objects are, the greater the force of gravity they have. In order to create this model of the star's orbit, here are the calculations that occurred. The net force was the force of gravity. This is found using the momentum principle, which tells us that net force equals the change in momentum over the change in time, which is really dp/dt. So F net equals dp/dt. As such, the components of F net equal the components of dp/dt. This is not shown, but the radius was found by getting the magnitude of the star's position, since the black hole was essentially the origin. So the star's position is the displacement. So the radius, star's mass, and force of gravity were all plugged into the law of gravitation to determine the mass of the black hole. As a side note, this also emphasized that a non-zero momentum is necessary for an object to be in orbit. All the previous equations were helpful in creating the code to make the computational model. A starter code was provided. It is the code labeled original. This was then edited in order to better model the motion of the star in the video. First, the mass was changed to the star's mass, then the final position was changed. The initial and final momenta were calculated along with delta P and delta V. Then, using the formulas from the previous slide, Fnet dp/dt parallel, Fnet parallel, dp/dt perpendicular, and Fnet perpendicular were changed. Then the law of universal gravitation was manipulated to get the black hole's mass. This code then calculated the black hole's mass at different times throughout the orbit. Through each run through the loop in the code, a slightly different mass was found. As such, these were averaged together to get the final mass, which is 8.65833 times 10 to the 33rd kilograms. Therefore, this model differs from what we observed about the mass of an object, in this case a black hole, in that it varied when in real life, mass is observed to be constant. This is likely since the mass of the star is determined using the net force, and the net force is changing throughout the orbit, since as the distance changes, so does the force. The mass will also change with the force, according to the way we're calculating it. To remedy this, one could use a star that has more of a circular orbit around the black hole. Therefore, the distance from the black hole is constant, and as such, the force acting on the object will be the same throughout, and therefore the mass will remain constant as it is in real life. To answer the question, the net force and its components are equal to the rate of change of momentum and its components. This can be seen by looking at the momentum principle, in which the net force is equal to the change in momentum over the change in time, which is the rate of change of momentum. However, although the values are the same, partially they let me look at the situation in different ways. The net force is the total pushes and pulls on the system, while the momentum is the amount of motion in the system. Therefore, the parallel and perpendicular components of force relate to the magnitude and direction of the pushes and pulls of the system, while the parallel and perpendicular components of the rate of change of momentum relate to the speed and direction of the motion of the system over time. So force puts my focus on pushes and pulls, and rate of change puts my focus on motion. If the motion remained the same, meaning velocity, momentum, and trajectory, I would not be able to find a different mass than I found originally because all the values I used to find the first mass would be the same. As such, I would return the same mass. However, there might be those very, very small differences through each mass calculations, like in the lab, but overall the mass would be the same. To conclude, this experiment showed that trajectory and motion of an object in orbit can be used to find the mass of the object it's orbiting, using Newton's second law of momentum and Newton's law of gravitation. This is helpful in finding the mass of objects we would otherwise be unable to determine or measure. Moreover, this emphasized the relationship between momentum and force, and showed that net force is equal to the rate of change of momentum, which is why momentum can be used to determine force. By taking all these into account, a computational model can be made to determine properties of an object, such as mass. However, it also showed that there can be discrepancies between real life and a model, which is why it's best to look at both models and observations to truly study and understand the principles of physics.